As ready as I'll ever be.
All right, let's get going for the last session of the week. So Nathaniel will tell us his last bit of his story.
All right. How's everyone doing? Woo! All right. So I know I'm the last thing standing between you and the most important part of Tazi, which is the weekend. But I will endeavor to send the lecture program of this first week of Tazi out with a bang. So we had a lot that we wanted to talk about. So let's just go ahead and get started. Do you remember where we left off at the end of my last lecture? We were sort of asking the question, OK, we have these 19 free parameters of the standard model. Should we be interested in finding a deeper explanation for any of them as a guide to thinking about more fundamental theory? And I developed this idea that I'd sort of phrased as the Hadoop paradigm that we can understand. We're sort of trying to understand these EFT parameters, generic outputs of a UV theory. And one thing we can do is we can understand, well, so a way to understand that is if they break symmetries, then quantum mechanics tells us that through RG flow, parameters will all be related to each other. Parameters that share the same symmetries or break the symmetries in the same way generally will be able to renormalize each other. And so typically they should be approximately the same size. And then we should just go through the list of symmetries that we can use to classify different parameters and carry out this analysis. And we started with dilatations, scale transformations, and we learned from that it just taught us about dimensional analysis. That told us that if we have a UV scale, all coupling should be sort of order 1 in appropriate units of that UV scale. And then we recognized, OK, there's more symmetries obviously at play. There's obviously all of the ordinary internal zero-form symmetries, all the global symmetries of the standard model that we've talked about. And from that perspective, we can understand, there are many parameters, for example, all the Yukawa couplings, which when we take them to 0, we restore at least a U1's worth of those global symmetries. And so we could understand if a microscopic theory broke those symmetries by a small amount, it's radiatively stable for that breaking to also be small in the infrared. But then we said, there's really 2 other symmetries that we hadn't brought to bear in this analysis. I'd mentioned this higher spin symmetry, and we hadn't brought that to bear at all. And then we hadn't brought to bear generalized symmetries. Now, I'm not going to have much to tell you about the generalized symmetries for an analysis because that, as a field, is still under development. That's not ready for Tazi this year. But I do want to tell you something about a higher spin symmetry and how we can use that for spiral analysis. Hopefully, at least you'll find the higher spin symmetry itself interesting. What I'll use it for in the end of the day is sort of like using a bazooka on a fruit fly. OK, we're going to use it to do a very slightly souped-up version of dimensional analysis. But really, what I want to do is put this idea of the higher spin symmetry into your brains so that you can think about it and do something much more magical. So just to give you an example of the higher spin symmetry, so really this is a symmetry of any free particles. This could be spin 0, spin 1/2, or spin 1 particles in 4 dimensions. They could be massive or massless. Let's just to illustrate the point, let's consider it with non-zero masses, because of course I think there's a fair bit that's understood about higher spin symmetry in the context of conformal field theories, and from that you might believe that the higher spin symmetry is unique to theories of massless particles, but it's true. The important thing here is that they're free, not that they're massive or massless. So just to give you an example, let's just consider the free real scalar field in d is equal to 4. All right, so we have our, don't even have to write subset. We can just write down, it's a very simple action to write down, right? And to see the symmetry, let's just Fourier transform. Let's work in momentum space. And so in momentum space, right, so I'll suppress all the factors of 1 over 2 pi to the 4th. We get 1/2 the Fourier transform of the field at minus p, right, p squared plus m squared, excuse me, minus m squared in these conventions, the Fourier transform of p. And we started with a real scalar field, but as you probably remember from Fourier analysis, in general, for an arbitrary real function of x, its Fourier transform is complex, but it has to satisfy a peculiar condition, which is that its complex conjugate is equal to the field at minus its argument. Okay. All right. But once we've actually written the action of the free field in momentum space, it becomes obvious what this enormous infinite dimensional higher spin symmetry is. We have the freedom to do transformations of the Fourier components of the field by complex rephasings, where here theta is just meant to be, it's my label for a function of p. And the only condition this has to satisfy for this to be a symmetry of the momentum space action is that this be an odd function of p. Right. This condition guarantees that the transformed fields still satisfy the constraint that comes from the Fourier transform. Okay. Good. So infinitesimally, right? This is just saying that small variations, small transformations go like I times this function theta p. And then we could go ahead and we could just imagine that this is some polynomial in p. We could write it as a series. And so, of course, it would be a sum over odd powers of momenta with some convenient normalization. Each one has a coefficient with some indices, and then these indices tie up, sorry, momentum space just powers the momentum. Okay. So hopefully it's clear to everyone, right, that the free action is invariant under this transformation, and all I'm now doing is writing the transformation infinitesimally and parameterizing it in terms of some series. Okay. So this is the point where we recognize that this is really a higher spin symmetry, because now we can take this to position space, and in position space, right, we see that as a transformation on the position space fields, this is just a sum of space-time derivatives acting on the field. All right. So you can go ahead, of course, and we can follow the usual Noether procedure, right? And we can construct the conserved currents for this. The conserved currents are even spin symmetric tensors, right, with even numbers of derivatives. Okay. Basically, the Noether procedure will tack on another factor of the field and another derivative, and that will give us these even symmetric tensors. Out of curiosity, so let's take, so the first term that would appear here for S odd in this transformation is just S is equal to 1. Does anyone have a sense of what that transformation is? We have another name for that. It's translations, right? So the S is equal to 1 piece of this is just translation. So what's the conserved current for that? Good. So and the stress energy tensor is the 2-index symmetric tensor corresponding to that we construct from the Noether procedure. You could then do it the next one for S, for S is equal to 3. That's just 3 space-time derivatives acting on phi. That's some 4-index symmetric tensor. You could go ahead and write that down. I've written down, I think I got it right in my lecture notes, but I'll leave that for you to look at later. There's nothing particularly enlightening about its form. But the important thing to keep in mind is that all of these currents that you construct, they're just conserved on shell. So they're conserved with the equations of motion of the scalar. And so there's some symmetrization procedure and subtraction of traces that you need to implement to make sure that the current is conserved on shell if it's massive. But indeed, it satisfies all of the conditions. And as a result, you generate an infinite dimensional tower of these conserved even spin currents. Okay. All right, so that's the infinite dimensional higher spin symmetry. In this case, we did it for a real scalar field. You could, of course, do it for fermions, and you can do it for spin 1 vector bosons. It is necessarily a symmetry of the free theory, right? So the Coleman-Mandula theorem tells us that we have to stop at stress energy if we want to think about conserved quantities in theories that have non-trivial interactions in d greater than 2. So necessarily, these are only conserved quantities for free theories. And so they're broken by any form of interactions. But we can go ahead and try to formulate a spurion analysis for it. All right, and so the spurion analysis is a little unusual looking. I want to emphasize this idea of formulating a spurion analysis. I've only heard this once before in some lectures by Riccardo Rattazzi. So this is full credit to Riccardo. The fact that, the fact that it doesn't appear in a paper, you haven't ever seen it in a paper, is just because Riccardo, takes forever to write things down. Riccardo, if you're watching this, feel free to write this down. But it's a very interesting idea, and it's one I think that's just dramatically underexplored. Now, I'm going to, again, use it as a bazooka to fire at a fruit fly, but once you know sort of what the idea is, in principle, there are much more powerful things you could put it to use. Okay, so to do a spurion analysis, again, we're going to work in momentum space because that's where the sort of transformation was most naturally formulated. And just as an example, let's consider phi-4 theory. Now, there's two ways to go about doing this. The way that Riccardo actually does it, these are in his GGI lectures from 2020. He actually does it by doing a spurion analysis for the higher spin symmetry of the massive real scalar and treating just this interaction as a spurion. There are some slight peculiarities about what he then uses that argument for. And so instead, what I'm going to propose that we do to illustrate the point is actually to do a spurion analysis around the higher spin symmetry of the free massless scalar. So that is to say, we're going to treat both the mass parameter and the quartic coupling as spurions. Okay. Good. All right, so let's go ahead and do that. So, of course, the things that we're going to treat spuriously are the mass parameter and the quartic coupling, which are very local in position space. In momentum space, right, this is going to give us, for the mass term, of course, we have two integrals over momenta. Now, again, normally what we do, right, is we do in the action the integral over position to get our delta functions, and we do one of the momentum integrals, but let's not do that for now. We just want to treat a full spurion analysis here. So we have both of these integrals over the momenta of the two phis. Then we're going to promote to treat it, what's the spirit of a spurion analysis, right? We take constant parameters of the Lagrangian, we promote them to things that transform covariantly under the assumed symmetries, and then we pursue the consequences. And so in this case, what that means is we're going to treat this parameter as some wildly non-local function of the momenta P1 and P2 of the Fourier modes. Okay. And then we'll do the same thing for the quartic coupling. So you know the game. Now we're going to have to integrate over 4 momenta. This now becomes, as a spurion, a function of all 4 momenta times the product of the modes. Okay. Good.
So when M doesn't break the symmetry, right?
So yeah, so this is why it's so good. So what I propose is let's formulate it as a spurion analysis around the infinite spin symmetry of the massless theory. So the masslive and the massless theory both have an infinite set of even spin conserved currents. The form of those currents differs, however. So when you construct it for the massive theory, there's a bunch of terms in that current that depend on m squared, and that's necessary for the currents to be conserved on shell. Whereas if I simply constructed it for the massless theory, all of those terms would vanish. And so what I'm proposing is we do a spurion analysis around the symmetry of the massless theory, so I can treat this also as a spurion. Ricardo has to, the reason I'm doing this is to avoid a certain step of hand waving that is present in Ricardo's way of making the argument. Okay. You can even tell him I said that. I'm sure he'll swear at me in Italian. But, okay. Yes. Yeah.
So your
Yeah. You had your hand up, right?
your M square is just the Fourier transform of M square with arguments being P1 minus P1.
Of course, indeed, what we normally do, right, what we did up here was, of course, we do the integral over x, we pick up a delta function and we use it, right? But I'm saying for now, let us not do any of that, okay? Let me simply treat this. Indeed, you could ask, what are the background values of these spurions, right? In the spurion analysis, we say we treat it as something transforming covariantly. We do a spurion analysis with it, and at the end of the day, we set it to its background value. So what are the background values? Well, the background value here is going to be m squared as a constant parameter, and then delta p1 plus p2. The background value of the spurion here is going to be lambda delta p1 plus p2 plus p3 plus p4. Right, those are the background values. But we're going to right now treat them as a spurion, so we can do spurion analysis and then see what relations we can obtain from that.
Why do you rule out introducing another like P3 to?
Oh, well, it's just the state. Oh, okay, good. So sorry, give me one more moment, and then it will be clear why I've constructed them this way. Okay. Well, there's one more question. So remember, what is the spirit of the spurion analysis? Sorry, so there's one more piece of information that I hadn't yet specified that motivates this choice. So we are necessarily going to introduce it as a function of the momenta, but now we have to assign it a transformation property so that these terms will now be invariant under the assumed symmetry, right? So in particular, we've said the symmetry that we want to study is the symmetry under which the momentum modes of our fields are rotated by some function of p. So obviously, if these are constant parameters, the symmetry is violated. But I can specify how they transform so that these terms will be consistent with the symmetry, right? So if we insist that this m squared is a spurion, so obviously this should rotate, because it appears with phi at two different values of the momenta, it should rotate in a compensating way. So that it compensates the rotations of the phis, right? And then similarly, the quartic interaction should compensate with 4 powers, right? Okay, and so that's why we're specifically denoting the dependence on the different momentum. Okay, so it's with those spurious charge assignments that even this will now even become a symmetry of the free massless higher spin theory, and this will become symmetric under the massive or massless theory. All right. Okay, so this is just a really interesting idea, and it's been, to my knowledge, not at all exploited. And it's sort of surprising that it hasn't been exploited because we've done spurion analysis for the sort of zero-form internal symmetries of particle physics for 50 years, 60 years. But this is living in the same equivalence class, right? We're asking what are the symmetries of the theory when we turn off the interactions, and let us simply do a spurion analysis in it. And this same thing we should also do. Now, I'm going to use it. Here's where the bazooka shooting at a fruit fly comes in. We could ask, for example, the question, now that we have these spurious transformations of the mass parameter and the quartic coupling in the theory, we could ask, for example, so again, what is the idea behind assessing whether parameters are 't Hooft natural or not, is we ask, for a given parameter in my EFT, what are the other combinations of parameters that I could make that would transform in the same way? And then we expect them generically to be of similar size. And so you could ask the question, okay, so this is in some sense the way that m squared transforms as a spurion tells us the direction in which it breaks the symmetry. What are other things that transform in the same way? Well, one thing that transforms in the same way is if I take the quartic spurion I take it with, so just to remind ourselves, this transforms under P1 and P2. If I take the quartic, of course, this transforms independently with 4 momenta. But if I take it evaluated where 2 of the momenta are back to back, then of course their phases cancel in this transformation. And this object constructed out of the quartic coupling with these background values, the momenta, transforms in the same way as the mass. And now we can do one more thing, so that's an interesting statement. And then on top of that, we can add back the dilatations so we can treat, of course, m squared and lambda as spurions of broken scale transformations, and we can add back that information. And from that, of course, the thing that saturates the transformations of m squared with respect to dilatations will be the UV scale lambda. So in totality, we should recognize that m squared as a spurion for the combination of dilatations and the massless higher spin symmetry of the theory transforms as the product of the quartic interaction and the square of the UV scale. Now, of course, you're thinking, gosh, couldn't I have just computed this Feynman diagram, right? So, of course, if I considered phi-4 theory as an EFT with a cutoff capital lambda, then indeed the mass gets a correction, which comes from using one insertion of the quartic. I close 2 of those legs into a loop. That's what this k and minus k is doing, right? Because this could be any values of k. We should sum over them. That's what the loop integral is doing. And on dimensional grounds, it picks up the UV scale. Okay. But the value of framing it this way, right, is the message of all of my lectures in some sense has been we can get tremendous power out of thinking about these field theories from the perspective of their approximate symmetries. And until Ricardo pointed this out a few years ago, no one had ever actually had a nice argument for how you get all of the parametric dependence, for example, in the scaling of a mass parameter. But this gives us something extra, right? This is on top of what we got just from the sort of dimensional analysis. Now we see, if the theory is nearly free, if the quartic interaction is very small, then it is reasonable to expect that we could have a mass parameter that is well separated from a UV scale. It's just the interactions are very weak, and it's because we've only broken the higher spin symmetry by a small amount. So, that's all I'm going to use this for today, but having put this into your head, what do I want to suggest you do with it? Well, there's obviously a much richer algebraic structure of the higher spin symmetry, which we haven't used, right? We've just used a very naive sort of spurion analysis to make one conclusion. One could imagine attempting to leverage the full power of the spurions with respect to the entire higher spin algebra, and there's really no telling all the sort of things that you could discover from it. Okay, but having understood at least a little bit how to think about spurion analysis for the higher spin symmetry, I want to come back now to the parameters of the standard model. And now we're in a position to ask ourselves, which ones should we be worried about, and should we try to explain in greater detail, or which ones could simply have been set in the far UV, for example, by string theory at the string scale. Okay, so there are some, we can make a little scoreboard. There are some parameters of the standard model that are Dirac natural. Remember, we said Dirac natural parameters are the ones, which are sort of order 1 in units of the UV scale, right? Depending on, and how many unit powers of the UV scale depends on the dimensionality of the parameters. Okay, does anyone want to give me some parameters of the standard model, these 19 parameters that seem Dirac natural? They're sort of order 1, in appropriate units of the cutoff. The Yukawas. Now I would say the top Yukawa certainly, right? Because that's basically 1. Now the electron Yukawa is 10 to the minus 5. That's maybe not Dirac natural, but it is going to be 't Hooft natural, right? So we'll come back to that later. So we're contrasting Dirac natural with the 't Hooft natural. Okay, but this is an order 1 number, and it's essentially marginal, so it has no extra powers of the UV scale, so that's definitely Dirac natural. The gauge couplings, right? G3, G2, even hypercharge. Hypercharge is a third. That's an order 1 number, right? If 2 is large n, then certainly a third is order 1. Other parameters that are, the Higgs quartic coupling, that's about an 1/8. That's not so small. So that's also another reasonably order 1 number. One of the physical mixing angles, so if we do the counting of the free parameters in the Yukawas, I left it in the lecture notes from that discussion, we end up with 3 mixing angles in one phase in the quark Yukawas. One of those mixing angles, the Kibibo angle, is sort of order 0.23, so that's also sort of a reasonably natural parameter. The other 2 mixing angles are quite a bit smaller. Okay, so these are all effectively order 1. Oh, and sorry, the phase that's allowed in the quark mixing, that phase as a number is about 1.2 radians, so that's definitely an order 1 number as a periodic quantity. So these are all just Dirac natural quantities. They just, if you write down any old generic theory in the UV, order 1 parameters, dimensionless parameters, there's nothing puzzling about them being that scale as you get to the IR. All right, what about 't Hooft natural parameters? So let's see, we've got of 19, now we've got 1, 2, 3, 4, 5, 6, 7. So we've got 12 more parameters to think about. Does anyone want to give me some examples of parameters that are 't Hooft natural? That is to say, they're parameters which violate a symmetry that is restored when we take the parameter to 0. So we can at least understand that if there was breaking of the symmetry by a small amount in the UV, it would remain a small symmetry breaking by the IR, and therefore there would have radiative stability of the smallness of these parameters. So I don't have any candidates. So you had mentioned the other diagonal entries.
I've heard the electron Yukawa.
Yeah, the electron Yukawa. Indeed, all of the other Yukawas, right? Because every one of those Yukawas breaks its own U1 chiral symmetry that's a subset of this U3 to the 5th. Okay, so all of the remaining Yukawas. So the quark Yukawas, right, that's, yi for I is equal to, bottom, charm, strange, up and down. It's also for the leptons, so the tau, the mu, and the electron. Okay, that's 1, 2, 3, 4, 5, 6, 7, 8. All right, we've got 4 more parameters to go. We have 2 more mixing angles. So the other mixing angles, theta 1, 3 and theta 2, 3 in the quark mixing matrix are parametrically small, but again, they come from breaking subsets of that U3 to the 5th chiral symmetry, so they're 't Hooft natural. Let's see, what else am I forgetting? We've got 2 more, okay? There's 2 more parameters. What's that?
The diagonal and Higgs mass should not be 2 natural.
Yeah, so we have 2 more parameters, right? So we have theta of QCD, and we have the mass parameter of the Higgs. Okay. Are these either Dirac natural or 't Hooft natural? Oh, good. Okay, everyone's doing the big nose. All right, great. So indeed, these are neither, right? So the Higgs mass squared parameter is, it's small in units of some UV scale, right? If we imagine the cutoff is high compared to the weak scale, it should be of order cutoff squared. It is not. There's no symmetry, no zero form symmetry that's restored when we take it to 0. Of course, you could say, well, maybe again, the massless higher spin symmetry is restored when we take it to 0. But as we've seen, right, if we violate that symmetry with couplings, then there's no reason to understand why this could be parametrically smaller. And indeed, there are many order 1 couplings in the standard model. And so if we repeat the higher spin spur analysis for the Higgs mass parameter, we should see that we expect it to be on the order of any of these order 1 couplings times the UV scale. And therefore, it's hard to understand why it's small. Yeah?
So are these 2 principles incompatible? Like the fact that there's some Dirac natural things that by the 't Hooft's principle should be small?
No. So good. So no, 't Hooft naturalis is a halfway house. Okay. So in the following sense. Ultimately, you might hope that indeed, sort of every parameter you see in the EFT is just some very generic output of a UV theory. But you might see small numbers, okay? And there's 2 possibilities when you have a small number. You could have a small number which could have been made small in the UV and stayed radiatively stable all the way down to the IR. Those parameters are 't Hooft natural. We can understand that they stay small because they're protected by an approximate symmetry, right? Then you could have parameters, but you might still want to explain why they were small in the first place, right? That's why the leopard has its spots, right? The challenge you face, you could have a great explanation, but it could live at the string scale, right? Nothing forces that solution to live in the infrared, okay? That's to be contrasted with if you have a parameter that is not 't Hooft natural, that doesn't restore symmetry when you take it to 0. It doesn't matter if at the string scale you've set that parameter to be very small. Radiative corrections on your way down to the EFT will make it large, okay? And so there, now you have two problems. You had a problem explaining maybe why it was small in the UV completion. But on top of that, you have a problem of explaining why it hasn't, the effective parameter, the infrared, hasn't become large. And okay, we could address this with a lot more field theory. They're just threshold corrections in an EFT all the way down. So every time you integrate out some massive degrees of freedom, they give threshold corrections to the ingredients in the EFT. And those are things that will change the Bayer parameter in the UV relative to the EFT parameter in the IR, proportional to all the scales that you hit.
Is the Tokugawa not protected by an approximate symmetry?
It is, but this just amounts to saying, this was order 1 in the UV and order 1 in the IR. So indeed, it's a lesson about the fundamental theory of nature. It's chosen to break one of the flavor symmetries of the standard model by an order 1 amount. So that's interesting. And in fact, that's an obstruction. You might say, let me have a theory of flavor where all standard model fermions are actually bound states of some strong dynamics. They're really baryons of some other physics that lives in the far UV. That's a very cool theory of flavor, except that it makes it very hard to understand why the Tokugawa is 1. Okay. Yeah, so these parameters just say these symmetries are broken by a large amount in the UV theory, and they remain large in the IR. These are ones that say, if they're broken in the UV, it's broken by a small amount. You could still hope to explain that, like write down a theory of flavor. But if you could have done it in the UV, and the fact that it shows up in the infrared is not a surprise. Okay. These parameters, even if you made them small in the UV, by the time you got down to the IR, they could become large. Actually, the statement is slightly different for the two of these parameters, and what I'll explain in a moment. But certainly for the Higgs mass parameter, there's no symmetry that's restored when I set it to 0. And even if I made it very small at the string scale, all of the mass thresholds that I crossed from the UV theory down to the infrared would give corrections to the low energy degree of freedom, its mass parameter. And it would be very hard to understand why this is small in the IR. Okay. So the fact that there's no symmetry that's restored when this parameter is taken to 0, and therefore it's very hard to understand why it's parametrically separated from UV scales, this of course is what we call a hierarchy problem. This has become a bit of a pejorative term these days because we didn't discover supersymmetry at the LHC, which is like a funny piece of sociology.
Or anything else.
Well, anyway. We did discover a Higgs boson. That was pretty cool. But,
Absolutely right. I mean, we didn't discover any other explanation for this, whether it was supersymmetry.
Absolutely. But supersymmetry, well, anyway, we could talk about let me briefly tell you some ways you might try to understand this and which ones are maybe more distressed by the LHC than otherwise. So just briefly, I promised myself these lectures would not be about the hierarchy problem, so I'm just going to say some things briefly. And really the reason I want to do it is there will be some lectures later on in TASI that will have formal methods that I think can be brought very interestingly to bear on the questions of why the Higgs is light. And so I just want to put some of these frameworks into your head so that when you hear from Sasha about the S-matrix bootstrap, you have an aha moment. Okay. So what are we expecting? So the Higgs mass parameter, again, if we just do the higher spin symmetry analysis, we would say the Higgs mass parameter, the higher spin symmetry of the theory is broken at an order 1 way by, for example, the Tokugawa. And if you do the spurion analysis, it'll turn out this goes like, for example, the square of the Tokugawa coupling, or it goes like the Higgs quartic, or it goes like the square of the weak gauge coupling, so on and so forth. These things all break the higher spin symmetry by the right amount to contribute to the mass of the Higgs. And then by dilatations, we should have the UV scale squared. And indeed, if you compute loop diagrams in an EFT with a cutoff, you reproduce precisely these corrections with order 1 numbers and loop factors in front of them, right? But what's nice about this is you can see it purely from the symmetries alone. So now you can ask yourself, okay, this parameter, now this is the mass parameter of the Higgs doublet. So of course, then after electroweak symmetry breaking, there's a factor of √2 that relates it to the mass of the physical Higgs. But the fact that we've seen a physical Higgs at 125 GeV tells us this parameter is about 90 GeV squared. And so you can ask, given that we also know all of these numbers, if we took this literally, right, if this were a generic output of our EFT, we would be able to identify what the scale should be. And we would say, lambda should be, once you put in these numbers and the loop factors, it should be about 500 GeV. Okay, so this tells us for the Higgs mass parameter to be a generic output of a UV theory, the theory should change from the standard model at about 500 GeV. And of course, we currently collide protons with center of mass energy is on the order of 13 TeV. And so we're definitely sweeping through the scale. All right. So what are some of the things that could have happened at this scale to make the Higgs mass parameter a generic output of a UV theory? Well, the first thing you might guess is we started my first lecture with the theory of the strong interactions, and we said, this dimensional transmutation gave us a condensate that breaks these chiral symmetries of the quarks down to a diagonal at a dramatically lower scale than the scale of quantum gravity. It actually turns out that the electroweak symmetry gauges a subgroup of those global symmetries. And so QCD in some sense would also break the electroweak symmetry if the Higgs didn't do it well beforehand. And so from that analogy, you could say, well, maybe I should think of indeed the Higgs actually, there's some other strong dynamics that breaks electroweak symmetry, and the Higgs is just an excitation of that condensate. So this is what's known as Technicolor, okay? So Technicolor, this is the idea that the Higgs is actually, in QCD, we would say it's the sigma meson. Sorry, let me write it as lowercase sigma so we don't confuse it with the pion fields, which is just like a real scalar excitation of the strong interactions. This was actually dead well before we constructed the LHC. This was dead in the 90s. The reason it was dead, there are several reasons. One of the reasons actually has to do with that custodial symmetry I told you about of the Higgs, right? The Higgs has this accidental SU2 cross SU2 mod Z2 symmetry. And strong interactions that break electroweak symmetry down to electromagnetism would violate that symmetry maximally. And the fact that precision measurements in the standard model were consistent with custodial symmetry killed Technicolor in the 90s. Okay, so 90s. But custodial symmetry was the reason. So you could say, well, let's do one smarter, okay? It doesn't have to be the case that that the Higgs itself is that some new strong dynamics breaks electric symmetry itself, and the Higgs is just an excitation. Maybe there's some new strong dynamics that has a global symmetry, and maybe the strong dynamics breaks a global symmetry in a particular way to make some Goldstone bosons that transform under the unbroken symmetry, and maybe then those Goldstones get a potential and break the remaining symmetry. So that is what's called the composite Higgs. Here the idea is that the Higgs is actually like some pions of some new strong dynamics. And that new strong dynamics has an SO5 global symmetry. This is the minimal picture. You can make it more complicated if you want to. But the minimal picture would be the strong dynamics has an SO5 global symmetry. And it develops some vacuum condensate that breaks that down to SO4. Okay? Now, SO4 is nice. This should remind you of custodial symmetry. And how many Goldstones do I get if I break SO5 down to SO4? Everyone's thinking about their special orthogonal 4. Good. All right. There's 4 Goldstones. That's precisely the number of real scalars that you could organize into a complex doublet of SU2, which is just gauging part of this SO4. Okay. So the idea behind this is there's strong dynamics. They're not breaking electric symmetry directly. Electric symmetry is a gauging of part of the global symmetry of the dynamics. The strong interactions break it down to make some Goldstones. And then there's explicit breaking of the symmetry that comes from the standard model couplings that violate custodial symmetry. So they turn these Goldstones into pseudo-Goldstones. They give them a potential. And then that potential induces further electroweak symmetry breaking. But this now gives you a mass gap between the scale of the Higgs mass parameter and the scale of strong dynamics, which has to do with the vacuum alignment of the Goldstones relative to the strong dynamics. And so this allows you to buy some parametric separation between the scale of the Higgs boson and the scale of the UV physics. It's not arbitrary because actually what you find is that the Higgs, if you just put in the custodial symmetry breaking the standard model gives you, the Higgs actually wants its VEV to be approximately the same scale at which the symmetry breaking happens. So you have to play some games to sort of make those scales separate. But what this means as far as looking for signs of what the UV completion is, the UV completion lives at a higher scale than it does in Technicolor. But now the Higgs really gets corrections to its properties that look like irrelevant operators in the EFT of the standard model. And now you can go ahead and look for those corrections. Okay, so in some sense, precision Higgs coupling measurements is one of the most interesting tests of this scenario. And this is under less stress than supersymmetry as an explanation for the lightness of the Higgs. But it's still something that is interesting. It's really happening right now, this search. The reason I wanted to give you this specific example is when we as phenomenologists write down, what are the signatures that we look at of this scenario at low energies, we write down an effective theory of this broken symmetry. The Higgs are some Goldstones. We put in the custodial symmetry breaking. We write down some operators. we don't really know what the spectrum of heavy resonances is, right? Because there's some unspecified strong dynamics. We could maybe speculate that it's QCD-like. That would give us some set of possibilities for where we should expect to see the excited states of these strong interactions. But we don't have a lot of control over strongly coupled four-dimensional gauge theories. Something else we can do is we can look to the lattice. So many of your local organizers actually have had a lot to say about interesting lessons for candidate strong interactions that would do this and the spectrum of states that would result. So that's a really interesting place where lattice has something to tell us. But the reason I'm pointing this out to you is that, again, in a week or two, you'll hear from Sasha about the S-matrix bootstrap. And you could ask a very interesting question, which is, if your low-energy particles are the goldstones that come from the symmetry breaking pattern, you can ask, in some sense, what is the allowed space in the scattering amplitudes, the 2-to-2 scattering amplitudes of these goldstones? And the S-matrix bootstrap, as you'll learn, you can not only describe that allowed space, but at least on the boundary of the allowed space, you can get access to what states have to be exchanged to uniformize the theory. And so that gives you some access to whatever the spectrum might be. And so that's really a tool that we might have to understand other non-generic strongly coupled dynamics that could be in the UV of this infrared description. So just to connect physics of the standard model to the S-matrix bootstrap, that's something to keep in mind when you hear from Sasha. OK, so this is still in play. The other option, of course, is supersymmetry. What supersymmetry is doing is it's trying to borrow a chiral symmetry, right? We said we can understand the lightness of all the fermions because there's a symmetry that's restored when we take their masses to 0, or their Yukawas to 0. Now, we can't directly apply chiral symmetry to the Higgs because it's a scalar. But if we had a symmetry that related the Higgs as a scalar to another fermion, that fermion's mass would be protected by chiral symmetry. And so chiral symmetry plus the symmetry that connects it to the Higgs would explain why the Higgs is light. And that, in a sentence, is what supersymmetry does. Okay, that's all I'll tell you about weak scale supersymmetry here. The challenge is, supersymmetry actually, it makes all of this sort of EFT logic calculable and extremely concrete. That is to say, if I supersymmetrize the standard model and I make the scalar partners of all the standard model fermions a bit heavier than the fermions themselves, that's a soft breaking of supersymmetry. But now I can actually calculate their corrections to the Higgs mass, and it precisely bears out this expectation, where instead of some UV scale, this now becomes the masses of all of these superpartners. Okay, so if you thought this was mumbo jumbo, if you write down a supersymmetric extension of the standard model, it becomes precisely calculable. Now the downside is that tells you should have superpartners about 500 GeV. We haven't seen them, and this is why there's despair about the fate of supersymmetry. But the message you should take away from this is, there's an interesting tension. We've seen the Higgs and a mass gap. There are very interesting ideas that have to do with strong dynamics where this could all make perfect sense. And so that's very much worth pursuing and bringing formal tools to bear on it. But it's also possible that we just haven't exhausted the space of ideas. Right? This whole analysis rests on zero form symmetries and, to a small extent, the higher spin symmetry of the theory. But maybe there's more symmetries at play that we could use. Yeah?
Not testable, but do you have an opinion on the anthropic reasoning?
So, of course, OK, right, you're making me say something on anthropics. So it is an interesting possibility. So anthropic reasoning is the idea that the Higgs mass parameter is non-generic because if it were dramatically larger than it is, we wouldn't have a universe with observers. And so because we're here to look at the universe, we've just selected a very unlikely corner of the landscape of parameter possibilities. So to turn that into a predictive principle, you need to imagine, of course, that there's a landscape of many different realizations of the standard model over which the Higgs mass varies. And then only for regions where the Higgs mass is very small, where we see it, can you actually build a universe in which there are observers. The strength of the conclusions you can draw from this idea depend on the strength of the assumptions that you make. So something that happens if you fixed all the parameters of the standard model, but you just allowed the Higgs mass parameter to vary from realization to realization in this landscape, you would in fact find that if you changed this mass parameter so that the Higgs VEV was more than about a factor of 5 above its measured value, that you would actually start to destabilize complex nuclei. Okay, so that you couldn't actually form all of the things that we ourselves end up being formed out of. And so you might say, oh, this is in fact a strong pressure, that the reason the Higgs VEV and the Higgs mass parameter is so small compared to some UV scale is that if it were actually more generic, nothing would ever form and we wouldn't see ourselves. But that conclusion, the strength of that conclusion, rests on keeping fixed all the other parameters of the standard model. In particular, if I also allowed the Yukawas to vary, in this landscape where I'm varying the Higgs mass parameter, then there is no boundary at which we've ceased to make observers. So, the confidence of anthropic reasoning, it's the strength of the assumptions that you put in is the strength of the conclusions that you draw out. It's absolutely could be what nature has chosen, But I think trying to have a predictive, reductionistic paradigm in the physical sciences has been tremendously productive over 500 years. And I'm not going to give up just yet, just because we didn't discover supersymmetry at the LHC. OK. Good. All right. That's all I want to say. Yes?
You say composite Higgs has a higher scale than Technicolor. Is there a rough scale?
Yeah, the scale of symmetry breaking should be a few TeV. So the heavy resonances could be at 5 or higher TeV. And we are only just now getting to that scale in direct searches. So it's, this we'll have interesting conclusions about composite Higgs from LHC data by the end of the LHC. But this is, in some sense, the most interesting game to play. And the thing, this is why something like the S-matrix bootstrap is interesting, because you could, what does it mean to say the scale is at 5 TeV? What do I expect to see at 5 TeV? Well, that spectrum of resonances, the states you expect to appear, their couplings, that depends on the strong dynamics. And so, right now we have some guesses based on analogies with QCD, but the space of strongly coupled field theory is vast. And so any other information we might have about what could happen at that scale would definitely guide the experimental program. So that's why, especially the S-matrix bootstrap, I think is something very interesting to apply to this question. OK. What's that? It's not that fast. So. Yeah. But anytime, like the inspiration for my lectures, right, was the statement that phenomenological challenges often inspire, dramatic developments in formal theory, and this may be, such a case. OK, that's all I wanted to say about the Higgs mass parameter. Of course, there's one more thing. Again, the spirion analysis we applied is a spirion analysis in the zero form symmetries, scale transformations, and higher spin symmetry. We haven't applied spirion analysis in higher form symmetries, in part because it doesn't really exist. It's not obvious how higher form symmetries could be brought to bear on this problem, right? So we remarked when we were talking about the higher form symmetries of the standard model that it does have an emergent one form symmetry in the infrared below the mass of the electron. So you might hope somehow there's a connection. Maybe if I took the Higgs mass to 0, that does something to that higher form symmetry. Unfortunately, it goes in the wrong direction, right? If I took the Higgs mass to 0, the Higgs vev starts to go to 0. The electron mass goes to 0. And so I'm suppressing the scale at which that higher form symmetry emerges. So it's sort of the opposite of 't Hooft's logic, right? There's a symmetry that is erased in the limit that the Higgs mass parameter goes to 0. But maybe one could be very clever and put that to use. I don't have any concrete ideas, but I just want to put that in your heads. OK. In the 30 minutes that remain, I want to now talk about this last parameter. And the reason I want to do it is, again, it is a beautiful playground to understand the occurrence of many of these forms of higher group and non-invertible symmetries that you've heard about from Hotat's lectures, from Clay's lectures, and from my lectures. So the state of this parameter, again, this is the theta parameter of QCD, as Hotat reminded you, this parameter violates CP symmetry. And one of the reasons, so experimentally speaking, again, we've noted this is a physical parameter. It shows up in various observables that we can go out and measure. One of the most distinctive observables is the electric dipole moment of the neutron. And our current bounds on the electric dipole moment of the neutron tell us that this parameter has to be less than about 10 to the minus 10. OK, so it's very compatible with being 0. It's a very small number. Now, you might say, well, that's at least 't Hooft natural, right? Because if I took it to 0, I would restore CP. But I don't actually restore CP in the standard model when I do that, right? Because I still have CP violation in the Yukawas. And that makes, and this is an order 1 phase, so it makes it very hard to understand, since CP was violated in the fundamental theory of nature, why it funneled itself entirely into this phase and not into this phase. In fact, the problem gets quite a bit more dramatic when we remind ourselves what happens when we consider our freedom to do anomalous global symmetry transformations in QCD. Okay? So to remind you of that, let's just go back to, again, our setup for QCD and the entry into the chiral Lagrangian that we presented in my first lecture. So again, let's just think about QCD. And at this point, when I say QCD, what I mean is let's already have broken electroweak symmetry. So we've now given mass to all of the quarks. They're now Dirac fermions. There's 6 of them if we include all of them. But then as we go down as a function of scale, we can integrate some of them out. And at most, 3 of them are light compared to the QCD scale. So let's just say, if by QCD we mean SU3 color plus some number NF of Dirac fermions. And again, in the UV theory, right, we have a Lagrangian where we can have mass terms for them. So putting these into NF component vectors, then we can pile up together the right-handed components of the Dirac fermion, conjugate them to make them left-handed Weil fermions, multiply them through the mass matrix with the left-handed components of the Dirac fermions. That's the mass matrix. And then, of course, we can have the theta parameter. And now, so if we think about the global symmetries of these fermions in the absence of the mass parameter, the symmetry, if we had NF of them, would be UNF cross UNF. That's just the freedom to do rotations of the left-handed Weil fermions and the right-handed Weil fermions that together make the NF Dirac fermions. And again, at least locally, so I'm not going to worry about the quotient, we can break this down to what we call the SU left NF, the SU right NF, and then the 2 U1 factors. So there's a vector combination, an axial combination. This is just baryon number, and this is then this last axial factor. And so as you may recall from your life in QCD, this axial factor has an ABJ anomaly. So there's a U1 axial SU3 color squared ABJ anomaly. And what that means is if we now imagine doing an axial rotation of the quarks, so in these conventions, those are rotations where we take, say if we rotate the left-handed Weil fermions by a phase, and we rotate the conjugates of the right-handed fermions by the same phase, that's the axial transformation. That activates the ABJ anomaly, right? So doing this transformation, of course, because we're rotating them in the same direction, that will actually give us a phase here in the mass matrix. And also because of the anomaly, it will shift the value of theta. So if we imagine doing this axial transformation, this will take our Lagrangian to a complex phase multiplying the mass matrix. And we will have shifted the theta term by an amount proportional to the phase of our rotation times the number of flavors. OK. So the reason I went through that exercise was, again, just to remind you, we can move around the theta term by doing axial symmetry transformations, but we can never completely annihilate a complex phase. It always lives in some linear combination of the mass matrix and the theta parameter. And from this, we conclude, in fact, there is a physical linear combination, which is invariant under the transformations, which we would call theta bar, which is whatever the term in front of GG dual is. And in these conventions, it should be minus the argument of the determinant of the quark mass matrix. So there's a physical parameter. And the reason I've bothered to write it this way is arg det m, right? This is equal to arg det the product of the up-type Yukawa couplings and the down-type Yukawa couplings is matrices, right? Because if I write the mass matrix, it has some entries proportional to the up-type Yukawas, some entries proportional to the down-type Yukawas. When I take the determinant, that gives me something that looks like a determinant of the product of the Yukawa matrices. OK, so somehow we're saying that this is basically 0, right? That's what the vanishing neutron EDM tells us. But if we ask, where does this phase live in the Yukawas, this actually invariantly turns out to be the argument of the determinant of yu yd minus yd yu. So it is extremely hard to imagine how a theory of nature would have made the phase that lives in this commutator order 1, while at the same time making the phase that simply lives in the product 0. Okay. People have built entire careers of model building trying to put a phase in one place and not the other. But I just want to emphasize this is why it's sort of a peculiar problem. It's not just that they're two CP violating phases, but actually if you ask what are their origins microscopically, they both come from very similar looking places. And so it's a great challenge to write down a fundamental theory of nature that sets one to 0 and not the other. Okay, so people's preferred mechanism for resolving this tension is to imagine that in fact in the microscopic theory, the CP violating phase that we measure is large, and the theta parameter is order 1 as a periodic variable. And then instead, something relaxes away the value of theta to 0 in our vacuum. All right, so that's the preferred solution. And the way that this is accomplished is with what's known as the QCD axion. So out of curiosity, how many of you feel like you know nothing about the QCD axion? I appreciate the bravery. How many people feel like you know something about the QCD axion? How many people feel like you know too much about the QCD axion? Okay, all right, well that's encouraging. Phenomenologists are definitely bosons, and right now there's a giant, in the US, there's a giant axion-shaped boson sun condensate in the phenomenology community, so it's easy to feel saturated with these ideas. So I want to tell you just a little bit about the QCD axion, but I don't really want to spend time on the phenomenology, then I want to actually take you to the generalized symmetries, because it's interesting as a phenomenological option for physics beyond the standard model, but I think what's even cooler is it brings to life in a very realistic setting in particle physics all of the richness of generalized symmetries that you've encountered this week. Yeah. Yeah.
How do we fix the coefficient 1 over 32 in the theta term? Because I feel in this week we see 8, 6, 2.
Well, so here I've always got the indices good. No, so I've tried very hard. If you take everyone else's conventions where they've been careful, okay, they typically have like a trace G wedge G.
I think that you can get factor of 2, not
No, yeah, from the G wedge G, and then they have a trace, they have matrix valued Gs, right? They have matrix valued Gs. So that gives you another factor of 2, because you're taking the trace of TA, TB, which is a half. Okay, so that's another factor of 2. And then I think I've got it right. Okay.
But maybe in the beginning, how do we fix 1 over 8? Like what?
Oh, then you're asking now you take the instanton density, right? You integrate that and you get an integer. Yeah, that's what fixes the rest. Yeah. So I am pretty darn sure I've gotten it right, and I'm the only one who's done it with indices. So, all right. Okay. Yeah. Thanks for the question. Okay. All right. So to motivate the axion, I don't want to do a lot of axion theory development. But what I want to do, well, in the interest of time, because we want to hear about generalized symmetries and axion theories, right? Right. OK. So to understand why an axion is a good idea, it just helps to understand what the theta dependence is of the QCD vacuum. I've actually derived it in a nice way, starting from the chiral Lagrangian in the lecture notes. So I encourage you to go take a look at that. Basically, we start from the same mapping we've done here, where we take the UV theory with the quark masses. Imagine you start in a theory that looks like this, where you have real quark masses and a theta term. You can now eliminate the theta term here by doing an appropriately chosen chiral transformation to set this to 0 and pop it back up in here. Now it's just a phase attached to the mass matrix. And we use our spur analysis to carry it from this down to the chiral Lagrangian. And then, right, remember in the chiral Lagrangian, the leading term is trace of the mass times the sigma field that has all the goldstones in it. We expand the sigma field, it's an exponential. The 1 in the exponential, that just gives us the vacuum energy. And that now depends on theta. So that gives us the theta dependence of the QCD vacuum. And so if you do that exercise, so I'll leave it in the lecture notes, you find that the answer is you can write it in terms of the pion mass, so something you measure, the pion decay constant, something else that you measure. And in a simplified approximation, where you treat the up and the down quark masses as the same, it just turns out to be proportional to cosine theta. crucially with a minus sign out in front. Okay, so you minimize the vacuum energy of QCD if theta is equal to 0. And you're probably sitting there saying, well, gosh, Nathaniel, why do we need to bother to dynamically set theta to 0? Energetically, theta wants to be 0, right? But of course, theta is just a parameter, right? It labels our theory. Okay, it labels the linear combination of winding number vacua that we take to define QCD in our universe. So there's nothing dynamical that can you pick out theta is equal to 0. But the idea behind the axion, if you just wanted to write it down to the level of the EFT, is to imagine you add a new pseudoscalar degree of freedom, which necessarily has to be periodic to match the periodicity of the theta parameter, which enters in the same way. So as a field, let's call it lowercase a. It has its own decay constant, so this quantity is dimensionless. If this has 2 pi f periodicity, has the same periodicity as the theta parameter, and this now multiplies GG dual. Okay. And now you can see, if you can write down a theory, well, this will pop out, then it should clearly be the case that the vacuum energy now, as a function of the theta parameter in A, is just going to be, in this analysis, it'll have the same overall coefficient. So again, you can do a rotation now that involves the axion to put all of these in the quark mass matrix, and you just follow your nose. And you see now that the vacuum energy goes like the cosine of theta plus A over F. And now we have a dynamical degree of freedom that can minimize the energy of the theory. And so the axion wants to pick up a VEV in the vacuum of the theory. It'll be minus whatever the bare theta parameter is in units of its decay constant, right? And so at this point, we will have minimized the vacuum energy. And as a consequence, we will set the overall theta parameter. Because the effective theta parameter that we measure from the neutron EDM is whatever the background value is plus this. And they've canceled each other. So it's consistent with not seeing a neutron EDM. Yeah?
To get the 10 to the negative 10 is called.
Yes.
So to get it, you have to tune this out.
You don't need to tune the F. No. It's whatever F is, right? That just tells you what the point is. The axion will relax itself to cancel. Now, what you need is other contributions to the potential of A. So in this hypothesis, this is the only contribution to the potential of A. If this is the only contribution to its potential, right, it will always relax the theta parameter exactly to 0. However, if this A has other contributions to its potential that don't appear in the same way, then that will move its minimum away from exactly canceling theta, and that will be a problem. So this is what's known as the axion quality problem. I could give you 2 Tazi lectures on it, but let's leave it at that. Okay, does that answer your question? Okay. Good. So this is why people care about axions, because it would be a beautiful way to understand the smallness of the observed theta parameter. But today, why we should care about axions is they really bring to life the structure of generalized symmetries. So let me give you 2 toy models. So building up to the QCD axion, we won't flesh out all of the complicated generalized symmetries of the QCD axion, but I want to give you 2 toy models of axions that give you all of the interesting substance in the sort of 12 minutes that I have left. And then I just want to finish with a small coda. Now I should say, you might think this is a very peculiar looking field to add, somehow to have it appear in front of GG dual. But actually, it's very natural if you have, for example, and we'll write down a UV completion in a moment, if you have an ordinary zero-form global symmetry that has an anomaly like the axial symmetry, and that's a real gold stone of spontaneous breaking of that symmetry, then it's very natural for the axion to appear to precisely like this and to have the periodicity that it needs. Okay. So the first toy model I want to give you to flesh out the generalized symmetry structure is just axion coupled to Yang-Mills, so let's not worry about quarks. So the idea here is we're just going to have a pure SUN gauge theory plus this axion field. And so good. So our Lagrangian is going to have in it now, in fact, to save ourselves time, we're just going to call it, we've already written it down up here. So axion Yang-Mills, we just imagine we have this, plus the kinetic term for the gauge field and for the axion. All right. So crucially, again, for the axion to appear in this way next to theta, for the action to be properly quantized, the axion has a periodicity under shifts by the axion by 2 pi times that decay constant times some integer. Okay? That will give it the same periodicity as the theta parameter. All right, so that means it's a periodic scalar, right? And I think, did Hotat mention in the litany of examples of theories that have higher form symmetry is the periodic scalar. So what was the higher form symmetry of the periodic scalar?
Winding symmetry.
Okay, Dan, you don't count. I mean, you do count, but I know you already know this. Anyone else? Okay, maybe Hotat didn't say it very emphatically. So this has two-form symmetry. Okay, so the periodic scalar So what is that symmetry? Well, the first thing we should do is we can ask, can I construct a 3-index antisymmetric tensor current? Right, that would be the appropriate conserved current for a two-form symmetry. And indeed I can. So here I'm not going to worry about the normalization because all of the formal field theorists are on the way to the airport. So they can't hurt me anymore. Okay, oopsie. Right, so I just take the Levi-Civita tensor with a space-time derivative. This is clearly conserved trivially. If I take another space-time derivative, antisymmetry kills it. Okay. So of course you can all, it's a fun game to play given some field, construct all the possible interesting conserved symmetries, conserved currents. The question is what's charged under it. But periodic scalars in general, they have string configurations associated with them. That is to say, they have vortex configurations in 2+1 dimensions that then if you translate them out in 3+1 dimensions are vortex strings. And now you can ask if that's a dynamical string-like object, its world sheet is two-dimensional, okay? And that is a candidate of the appropriate dimensionality to be charged under a two-form symmetry. Okay, so the charge objects, if you imagine taking an infinitely heavy string and sweeping it out through space-time, then I would get some two-dimensional object as its world sheet. And that is the thing that links with symmetry defect operators to define the two-form symmetry. All right. If you want to think about it concretely, again, if you got a goldstone by breaking a U1 symmetry, then it's very clear those have vortex solutions in 2+1 dimensions that swept out make global strings in 3+1 dimensions. And that's precisely an example of this. All right, so it has a two-form symmetry. It also, of course, has a zero-form symmetry. That's just this. This is a non-linearly realized zero-form symmetry acting on the axion. We're not really interested in the zero-form symmetry in this discussion. And there's one more higher form symmetry in this example. Does anyone who's not Dan, because I know he knows the answer, want to speculate as to what the other higher form symmetry is? It's a one-form symmetry. It's a center symmetry, right? So we've said this is SUN Yang-Mills. So we have no charge matter, and so that means there's a ZN center. And so we also have a ZN one-form center. Okay. So it turns out there's a mixed anomaly in this case. So we encountered, when we talked about two-group symmetries, right, we realized when we have a mixed 't Hooft anomaly and higher form symmetries of varying degrees, they can combine to give us a higher group symmetry. In this case, we have a two-form symmetry and a one-form symmetry, and there's a mixed 't Hooft anomaly that's related to the ones that Hotat described. I'm not going to describe it in detail here for the interest of time, but that actually causes the center symmetry and the winding symmetry to participate in a three-group. So that's cool. You can, again, the rule is the largest symmetry is the two-form symmetry, so we add one, and that's what we call the resulting symmetry. You can demonstrate its properties by doing everything we did in the two-group case, turn on background gauge fields coupled to the conserved currents, see what happens in the transformation to reveal the structure. The thing I want to emphasize in this example is this also comes with its own version of emergence inequalities, right? We said in a higher group symmetry, there's a good symmetry and a bad symmetry, and the good symmetry as a function of scale should always appear before the bad symmetry. Okay. That's precisely the case in this example. The winding symmetry of the theory should appear before the center symmetry of the theory appears. I've written down a perturbative UV completion in which you can see that very concretely. In the interest of time, I'll leave it in the lecture notes for you. But I want to give you a very general argument for why this should always be true. Okay? And the very general argument is the following. So Hotat also mentioned the idea of anomaly inflow. So you could have a theory in some bulk number space-time dimensions, which has some defects or objects of lower dimension living in it. And naively speaking, it can look like there should be anomalies associated with those lower dimensional defects. But because the whole theory is anomaly-free, something must appear on the defects to cancel the local anomaly. And this is the phenomenon of anomaly inflow. And so in this particular case, indeed, we get anomaly inflow. Basically, the idea is this term that couples the axion to GG dual guarantees that in the presence of a global string, for example, that's dynamical, that would break the two-form symmetry, in the presence of this coupling of the axion to GG dual, there are now fermionic zero modes that live on the string that are charged under the center symmetry. And so they break the center symmetry at the same scale that the two-form symmetry is broken. So again, this is an example where the emergence inequalities remind us of a beautiful non-perturbative phenomenon, that anomaly inflow, that has to come in to rescue us and satisfy the emergence inequalities. Okay. I fleshed out that and details of a perturbative UV completion in the lecture notes. But I want to give you one more example because you've just learned about non-invertible symmetries in 3+1 dimensions. So we should absolutely see a situation where that plays out. And so I want to give you another toy model, which is also a component of the real axion you would couple to the standard model. And that example is axion Maxwell theory. So axion Maxwell, you might say, gosh, that's going to be simpler, isn't it? Right? Yeah. So now we're just taking our gauge theory and we're making it abelian. So now we're just going to imagine we have an axion coupled to an abelian field strength. So naively, this theory, again, you think is much simpler. But as we know, right, Maxwell theory has a very rich set of continuous higher form symmetries. In fact, in this case, there are 4 interesting symmetries. So we still have the zero form shift symmetry, so the axion zero form symmetry. Right, and so the conserved current there just goes like the derivative of the axion. Does anyone want to give me one of the remaining 3? Again, not Dan, I'm sorry. Before we think about what the anomaly, what this interaction does to them. So if I turn this off and I have a periodic scalar and Maxwell theory, what would my higher form symmetries be? Good, so we still have the axion two-form symmetry. Right? Yeah. With the electric and magnetic, good. We have the electric, so this is the Maxwell, the electric, and the magnetic one-form symmetries. Good. So those are just the symmetries of the free Maxwell theory. Now we've turned on this interaction. We break 2 of these symmetries. So 2 of the symmetries here are good. 2 of them naively are broken. That is to say, their currents are no longer conserved. Does anyone has a guess as to which 2 are broken? So the electric one form is broken. That's good. And that just follows. So we would normally say the electric one form symmetry, the current is conserved by the equations of motion. Now if we apply the equations of motion, right, so the divergence of that current, now that gives us something that's proportional to A and F dual. In fact, a derivative of A and F dual. Okay, indeed. So it's no longer conserved by whatever's happening on the right-hand side here. What other symmetry breaks? The shift symmetry breaks, right? The shift symmetry breaks just because we have this anomaly term, right? So if I take the divergence of this current, now by the equations of motion for the axion, I pick up FF dual. So the divergence of this thing So now we have a very rich structure. In fact, the rich structure, as Clay has now primed you to understand, the resulting surviving structure, we have 2 good symmetries. So the 2-form winding symmetry and the magnetic 1-form symmetry are both good symmetries of the theory. The 0-form symmetry and the electric 1-form symmetry are non-invertible, right? So this is exactly like Clay's example, where I've had some 0-form symmetry current that now, due to an anomaly, I recognize is intertwined with the magnetic one-form symmetry. And this is a slightly fancier example. This is now a non-invertible one-form symmetry. And it's become entwined, actually, so you could move the Levi-Civita tensor either direction. It's become entwined with the two-form symmetry and the magnetic one-form symmetry. So if you were to write out the fusion algebra, you would have symmetry defect operators of both of those symmetries appearing on the right-hand side. And non-invertible symmetries, like higher group symmetries, have these emergence inequalities associated with them because there's a good symmetry and a bad symmetry. And now there's two sets of them. There's an emergence inequality that tells you the magnetic one-form symmetry should emerge before the shift symmetry. And the physical phenomena that guarantees that, actually, is that if you have monopoles, which would break this symmetry, loops of the monopoles give a potential for this axion. And so, in fact, they violate the zero-form symmetry. That was only computed a couple of years ago. So we're learning things in real time. Similarly, the non-invertible one-form symmetry, now that ties it up both with the magnetic one-form symmetry and with the winding symmetry. And so it tells us this symmetry should emerge below either of these, the lower of these two scales. And indeed, that's also what happens. Because we have this term, magnetic monopoles actually get dionic excitations. So if there's a monopole which would break this symmetry in the presence of this anomaly term, it gets electric excitations that break the electric one-form symmetry. And similarly, if we have axion strings that become dynamical to break the two-form symmetry, because of this anomaly term, anomaly inflow gives us electrically charged zero modes living on the strings that also break the electric one-form symmetry. So this is just a beautiful example, right? You really see in real time how the structure of generalized symmetries plays out and how there are physical dynamical consequences that remind us of non-perturbative phenomena. Now, we've known about most of those non-perturbative phenomena for quite some time. In some cases, for example, the breaking of an axion shift symmetry by monopole loops, we didn't really know about that until the last couple of years. But even the things that we knew about are now organized in a very systematic way. And that picture was lacking, for example, in the 1980s when anomaly inflow and monopole catalysis were first worked out.